Morning. Start.
Start.
Good morning. In this class, we're discussing about the case study of the finite element analysis in dynamic analysis. As we learn about the DT-based class, we have to study the empathy and ideate prototype. So now we can apply the real-time application of the finite element applications into the sample. So let's discuss the topic detail.
So, myself, Hari Krishna. Today we are presenting a forensic engineering case study titled Silo Support Beam Resonance Crisis. This case study focused on how industrial vibration cause structural resonance is large storage silo system, leading to serve beam stress excessive oscillations and partial structural failures. The analysis was carried out using finite element analysis, specifically model analysis, harmonic response analysis, structural stress evaluations. The industries involved was bulk material handled on elevated supported beams. Initially, the structure appeared safe under static load conditions. However, during the continuous machine operation, abnormal vibration began to occur. Operations observed loud humming sound, excessive beam shaking, bolt loosening, surface crack near build joints. After several weeks, one of the support beam developed fatigue cracks. Company then initiated a forensic structural investigation to identify the root cause of the failure. So, next heading is problem identification and engineering theory.
So now we'll see the problem identification and then engineering theory. The investigation team first examined the operating conditions of the silo system. This silo was supported by a 4 steel I-section beam and connected to rotating conveyor machinery operating continuously at high speed. The major suspicion was resonance. The resonance occurs when the excitation frequency of a machine matches the natural frequency of the structure. And when this happens, the vibration amplitude increases dramatically. So this results with the engineering team, therefore, performed a model analysis to determine the natural frequencies and the mode shapes of the support structure. In model analysis, the governing vibration or the equation is k minus omega square into m psi is equal to 0. Here K is a stiffness matrix, M is the mass matrix, omega is the natural frequency, and psi represents the mode shape. Here, with the help of FEA software, we identify the first natural frequency of the support beam structure was extremely close to rotating motor frequency. This confirmed that there is a high possibility for resonance. So this first mode shape lateral beam oscillation, especially near welded support regions. I request next person to continue.
Okay, now we will check about model analysis, that is FEA simulation model analysis. My name is Sachin Kumar. I am here to present the model finite element analysis. The diagnostic core of this investigation, we modeled a W200 by W100 beam with the fixed boundary conditions at the support using a hexahedral dominant mesh of approximately 85,000 elements. We then performed a model extraction to identify the beam natural frequency. The results were alarming. The mode 1 lateral bending occurred at 23.8 Hz. Mode 2 vertical bending 24.6 Hz. Our motor excitation frequency is 24.4 Hz. The motor frequency sits precisely between mode 1 and 2. This is a structural resonance. The beam was being driven at frequency that matched its own natural vibration modes, amplifying deflections far beyond any static analysis would predict. The FEA deformation plot on screen shows the midspan displacement under resonance. The red region is not just a structural concentration, it's a being singing itself as a distraction. Number 4 can continue.
So, I'm T. Sriniti. I present the failure analysis and root cause. The forensic investigation combined simulation results with physical inspection findings. Crack patterns observed in the reef structure matched the high-stress regions predicted in the FEA model. The primary root causes identified were resonance between mesh frequency and beam natural frequency, insufficient structural damping, poor reinforcement near welded points, long-term cyclic fatigue flooding. Repeated oscillations caused progressive fatigue crack growth. The fatigue phenomenon can be explained using cyclic stress behavior, where repeated loading reduces structural life even below yield stress. The harmonic analysis also revealed that vibration amplitude increased continuously during prolonged operation. Eventually, weld joints experienced microcrack initiation followed by crack propagation. If the failure had continued unnoticed, complete collapse of the silo support structure could have occurred, risking worker safety, production shutdown, and economic losses. Therefore, immediate corrective action became critical.
So, myself, Nishant, and I'm going to speak about the solutions, improvements, and for the conclusion. Based on the forensic analysis, several engineering modifications were recommended. First, the support beam stiffness was increased by adding reinforcement plates and cross bracings. Secondly, vibration isolators were installed between machineries and structural supports to reduce dynamic force transmissions. Third, operational motor speed was slightly modified to avoid resonance frequency overlap. Additionally, damping pads were introduced to absorb excess vibration energy. After redesigning, the structure was reanalyzed using FEA. The new model frequency shifted away from the excitation frequency range. Harmonic response results showed a major reduction in vibration amplitude and stress levels. This case study demonstrates the importance of considering dynamic loading effects during structural designs. Static analysis alone is not sufficient for industrial systems subjected to continuous vibration. Using model analysis, harmonic analysis, forensic fail investigations, engineers can correctly predict resonance-related failures before catastrophic damage occurs. In conclusion, this study highlights how finite element analysis plays an important role in ensuring structural safety, reliability, and industrial risk prevention. Thank you.
Thank you.
Thank you, sir.